Christopher Nolan wanted the most accurate black hole ever depicted on screen, so he hired the man who actually models black holes for a living, and what they produced is still shaping astrophysics research a decade later. The film is Interstellar. The black hole is Gargantua, and the story of how it was created is one of the most unusual collaborations between Hollywood and science in the history of cinema. Kip Thorne is not a movie consultant. He is a Nobel laureate in physics, a former Feynman Professor of Theoretical Physics at Caltech, and one of the world's leading experts on general relativity, black holes, and gravitational waves. He was the scientific advisor on Interstellar, and the co-producer credited with ensuring the film's depiction of relativity was as physically accurate as possible. Thorne had been working on the mathematics of black hole accretion for years before the film. He and his team had developed algorithms that could solve the equations of general relativity for what light would do as it passed near a rotating black hole. The original goal was research, not cinema. When Christopher Nolan approached Thorne to design the visual appearance of Gargantua, those research algorithms were adapted directly into the rendering software Double Negative used to create the film's visual effects. The result, published in a 2015 paper in Classical and Quantum Gravity, co-authored by Thorne and the visual effects team, produced a black hole surrounded by an accretion disk where the image of the disk appears warped, looped over and under the black hole's shadow. This visual feature was not artistic license. It was a direct prediction of general relativity. Light from the far side of the accretion disk actually loops around the black hole and appears above and below the shadow because the gravitational field bends the light trajectories. In the film, the planet Miller's Planet is depicted orbiting so close to Gargantua that 1 hour on its surface corresponds to 7 years passing elsewhere due to time dilation. The physics of this is real, but requires extreme conditions. To produce that magnitude of time dilation without tidal forces destroying the planet, Gargantua must be a supermassive black hole rotating at very near the maximum possible rate. A black hole can, in principle, have an angular momentum approaching the limit predicted by Roy Kerr in 1963. At that maximum, the innermost stable orbit of an accretion disk moves much closer to the event horizon than it does for a non-rotating black hole, reducing the tidal forces at the orbit where Miller's Planet would be safe. Thorne's analysis in his book The Science of Interstellar shows that to sustain a planet at that orbit, with 1 hour to 7 year time dilation, the black hole needs to be approximately 100 million solar masses, spinning at the maximum theoretical rate, and viewed nearly edge-on to produce the warped accretion disk. The accretion disk itself is also physically grounded. Real accretion disks around supermassive black holes reach temperatures of millions of Kelvin and emit most of their radiation as ultraviolet and X-rays, not visible light. The film's glowing disk is artistically exaggerated, but the disk's behavior, including Doppler beaming, where one side of the disk appears brighter than the other due to its motion toward and away from the observer, is rendered accurately. The same Doppler effect that makes a police siren sound higher when approaching and lower when receding also makes one side of an accretion disk appear brighter in real astrophysical images. The tidal waves on Miller's Planet depicted as shallow water waves are one of the few details the film has been criticized for scientifically. Realistic tidal waves generated by a black hole at the required orbit would be more like planet-ripping bulges, not surfable waves. Thorne has acknowledged this in interviews, citing the need for dramatic storytelling over literal accuracy. The wormhole used to reach Gargantua in the film is a Morris-Thorne wormhole, a theoretical construct proposed by Thorne and Mike Morris in 1988. Real wormholes of this type are solutions to Einstein's field equations, but they require exotic matter with negative energy density to remain stable. No such matter has ever been observed, and there is no known natural mechanism that would produce one. The film's depiction is mathematically valid as a solution, but physically implausible as a naturally occurring object. The visuals from Interstellar have entered the scientific literature. The warped accretion disk around Gargantua was used in academic papers and educational materials because it remains one of the most intuitive and accurate depictions of gravitational lensing of an accretion disk ever produced. In 2019, the Event Horizon Telescope released the first image of a real black hole shadow. The the supermassive black hole in galaxy M87, and the visual was remarkably similar to Gargantua, validating the underlying physics. Nolan's commitment to accuracy produced a film that doubled as a research tool. The line between cinema and science has rarely been so thin. Follow for more on the science behind your favorite films. And tell me, knowing how much real physics is in Interstellar, do you think the film changed how the public understands black holes?